I think now this is kind of a recap on the whole accelerated life testing. So what we have already discussed. So I'm going to go through these next 4 or 5 slides quite rapidly, because I think we already have covered all those things. Now there's one question in the chat. There was something about thermal resistivity. It increases with the test of the same product or by changing the material. The thermal resistivity in Joonas' presentation means that when the cyclic loading causes delamination or crack propagation, either in the die attach, solder, or system solder. So there's basically 2 solder interconnections there, which are both very large. And if we look from the top, so we have the dies. The power dies are soldered from the backside to the ceramic substrate, and then the ceramic substrate is soldered to a heat sink or let's say base plate with the solder interconnection. So both these solders, when you have cyclic loading, they start to, let's say, delaminate, or cracks start to grow from the sides, and that makes the thermal resistance of these certain layers to increase, and that means that you can see it, for example, in the structure function. Joonas had this example that at the beginning the structure function had a certain shape, so thermal capacitance versus thermal resistance, and after a certain amount of cycles, the curve have kind of swapped towards right, because this thermal resistance had increased. So basically, this thermal capacitance kind of indicates that how far you are from the actual source of the power losses. So it's kind of a distance, of course, not the linear distance, but it all the jumps in the thermal capacitance are referring to certain interface. And now, if we see that at certain point the curve has kind of moved towards right, it means that the resistance, which is on the x-axis, have increased at the certain, let's say, distance from the power source, and that means that one of these, either of these, let's say, solder interconnections have delaminated, so you have less area where the heat flux can go through. It means that your thermal resistance has increased. So it's a change of material in that sense, that the material has lost some of its area which can conduct heat. Okay, good. Yes, so just quick summary. So basically, in order to design a test, so if you start from the beginning, so you don't have any standard or anything, you would kind of start thinking, okay, what kind of accelerated reliability test I should design. Then of course you need to, let's say, define certain things. First of all, what is your acceptable failure rate during the service life? Basically, again, this constant failure rate over the useful life, because that defines your failure criteria, how many failures you can basically accept per time when it's not a question about the wear out. Then you identify the actual use environment. So what will be that? And then you combine the use environment with the internal stresses. So if there are some power losses or whatever coming from the product itself. Like in Joonas' example, there was this delta T, this thermal cycling, which is coming from the use environment, and then the power cycling, which is coming from the actual product usage itself, based on the let's say, the operation of the product itself. Then, based on these stresses, you identify the failure modes and mechanisms. So you guess what could go wrong, and then you develop a model, like use the Coffee-Manson model or whatever model, in order to describe this behavior, this mechanism during the testing and as well as normal operation, and then you have the acceleration model. So based on the model, you can then let's say decide the test parameters. So what would be the test duration, what kind of average temperature I should use, and so on. And then you carry out the test, and then you analyze the failures, and of course you need to confirm that your guesses were correct. So you ended up having these failures, which you made the model, which you used to predict the let's say conditions for the testing. So if you end up having some other failures, then all these were not correct, and then you need to start again. Either you modify the test so that you end up in this kind of thing, or then you really consider again, was my let's say prediction wrong, and in fact these failures which we saw from the test are really the relevant failures. And then you can of course use statistical mathematics and everything to really understand what this means. So how many samples you need to test in order to have certain confidence levels and so on. So the main thing is that you assume that there's a relationship between the stress and the resulting life. And it could be something like this. It could be something like this. So here is just another form of Copy-Manson equation. So what this means is that the applied stress is basically here. This is the plastic strain. So every cycle, when you cycle something, some part of the device is going into plastic region. So their plasticity means that there's a permanent mechanical deformation. And how much that is with a single cycle is proportional to the cycles of failure, which is here the n value. And the rest are basically constant. So this is just a constant, and this is something which is related to the material itself. I will come back to this later on, so don't worry. This is just an example that you need to know the relation between the stress and resulting life. Either it's the number of cycles, or it's the time to failure, or it's the acceleration factor. And it is based on the physics of failure. So these are all more or less failure physical models, because they have some kind of a correlation between the material parameters. So for example, this one here, this is related to ductility of the material. So how much cyclic bending it can withstand. So you know the relationship between the applied stress, or relationships like here. So what is the ratio between delta T in the test conditions and delta T in the field conditions, or frequency, cycling frequency in the field versus test conditions, or maximum temperature in the field versus test conditions, and so on. So you have some kind of an equation. And then you do the testing so that you use test vehicles which mimic the actual components. You shouldn't use too complex products, because they are really difficult to then monitor and analyze, but you should also, your test structure should be, let's say, relevant from the actual device point of view. And here, again, would like to emphasize the modeling, the power of modeling for simulation. So for example, you can for example have your complex let's say printed circuit card, and then you know that, okay, this is the critical component, and then you model that the complex card and try to define that, okay, what kind of cyclic loadings locally this critical component will see in this kind of a structure. Then based on that data, so stresses and strains as a function of location, you can design a test board, which for example contains, let's say, 15 of those identical components. So for example, 3 to 5 matrix, and then you design the board as well as the test, so that the testing is causing similar type of stresses for these individual components than the one component which would be on the real product. So then you get basically, with a single board, you get 15 data points. So you get more statistics. And that's really helpful in let's say, minimizing the needed time and money for testing, because that's, of course, always, even I have not mentioned in every slide, but basically it should always be remembered that, okay, accelerated live testing, the durations are hundreds of hours, even thousands of hours. So weeks or months, that's time consuming and cost, let's say, needs financial resources, and also you need significant amount of samples, meaning that because you need to have the statistics there. Again, in health testing, you could do the health testing with just one single unit, one single product. You just refix it and repair it and make the corrective actions and start again the test. But with the ALT testing, you need to have the statistical confidence levels. So you need to have, let's say, 15 data points or 30 data points or whatever for every single component, every single test. And that's also costly, can be costly if you are testing something like, let's say, displays, which still every display has a certain cost value. So maybe 10 euros or whatever, 20 euros, even more, if you're talking about very large ones. But you can utilize this kind of an approach that you have similar components. So you don't need to manufacture 15 test boards and all test boards have just one component, but you have these 15 test components. And you can also simulate the actual components. So if you are interested in the, let's say, for example, the processor of your laptop, that would be the critical. You take a component which mimics that. So it basically has the same structure, same I/O, same way of soldering, similar size of silicon inside, but it's a dummy one. The cost might be 1/10 or even 1/100 of the actual processor component, because you don't need the semiconductor processing. You just need a dummy silicon chip and maybe some daisy chain connections inside. So you can utilize test components. And there are companies who are, let's say, selling test components just for these purposes. Okay, few cautions. So I think I have already mentioned all these. Maybe this is just a recap in that sense. So monitoring is important. This is, I have highlighted both in health testing as well as ALT testing. So you need to monitor your product, because if you have a situation that you have, let's say, 100 test pieces, you put them in the test, then you run a standard test of 1,000 hours, and then after the test you measure them and you see that half of the products have failed. What does it tell you? It only tells you that half of the products have failed, but you don't have a slightest idea did all the 50% or 500 components fail during the first 10 hours or during the last 10 hours, because that's, of course, very, very different. Either you have the decreasing failure rate or you have the increasing failure rate, and the mechanism could be completely different. So therefore, you need to have a monitoring. Here is maybe a little bit exaggerating, let's say, statement that use of standard test. So, but the point is that if you use a standardized accelerated test, then you need to understand why you are using it and how you are using it. So of course, some standards are, let's say, obligatory. So in order to qualify your product for a certain purpose, like automotive AEC, you need to show that you have passed. So then it's go, no go. You need to run the test and see that, okay, all are failed. None of the components failed or products failed. So I have passed this test. But it does not, let's say, help you in understanding in any way if you don't end up any failures. So testing until failure is, of course, gives you more information than just testing according to a certain amount of time or values, and time or cycles. Then standardized tests, some standards, let's say, clearly define that, okay, this is your maximum temperature, this is your minimum temperature, and this is your ramp rate. And then, of course, you need to do along that. But then you have also some quite much other standards where it is left to you to decide. So, for example, there's a different categories. So if you say that, okay, now we have done according to this standard class A, meaning that you have used this and this temperature, glass B would be another test conditions, or then there is a, let's say, value which you can define based on your own product and operational conditions. So, for example, these IEC, International Electrotechnical Commission standards, which are global standards, basically, which can be utilized for whatever purposes, they are more guidelines. So you can modify the parameters in that sense that you can agree with your customer, or you can just use whatever parameters, whatever in quotes, but you need to report. So, okay, we did this test according to the standard, and we used these and these and these parameters. But on the other hand, we have these like AEC automotive tests, which really you cannot, let's say, change anything. You just need to do according to that standard. This is what I already discussed a minute ago. So the test vehicle, what you use is important, so that it's not, let's say, adequate, which mimics the actual product, but it's not too complex, so that you would, for example, not be properly monitoring it, or you cannot do the failure analysis. So doing the failure analysis is always extremely critical to verify that your assumptions were correct. And maybe this is mostly some generic stuff. Maybe I will highlight only this one. So these cumulative failure models, or let's say failure models in general, you need to understand how these models were defined and under which conditions they are applicable. So for example, in Joonas's presentation, he showed how to use this Miner's rule. So these cumulative different types of thermal cycles, and how you basically, let's say, calculate, sum up these damages to get really the actual lifetime of cycles to failure in when you have different types of cycles, how you can calculate that. And that is applicable typically for metals, because and metals in certain, let's say, stress range, so that the failure mechanism stays, for example, high cycle fatigue or low cycle fatigue, or whatever is the mechanism which one wants to model. But you cannot use the same model, let's say, for example, plastics, or in fact you cannot even typically you cannot use the same model even for ceramics, because ceramics do not have this plastic area, which is critical, for example, in Coffee-Manson equation. So, which is kind of the baseline for Miner's rule also, because that's kind of anyway the cyclic fatigue, which is behind the Miner's rules. So you need to understand your models and how you can utilize them. So quite often the problems comes when somebody has developed a model. It's a, let's say, a combination of analytic and failure physical model. So it has some, let's say, statistical parts, or it has some analytic parts in that sense that they have just fitted some real depth values to the equation, and then it might have some physical parameters there, like material properties or whatever. And then you start using that one somewhere else, some other stress conditions or some other types of materials or structures, and then it might be that you are going completely on opposite direction, wrong direction. It might be that it's still valid, but it may not be. So this is what you need to be sure that you understand what are the, let's say, the basic requirements behind the models. Okay, so then let's kind of the main point of today, which is not very long, just a few slides, is the screening. So now we are here. We have finalized our design assessment reliability testing. We have finalized our design maturity testing. So we are sure that our products are reliable enough. And now we start with mass production, and then we just need to follow what is coming out from our production line. So we are going to screening, monitoring the production. So there are several different names and acronyms, basically all mean the same. So it's highly accelerated stress screening, it's environmental stress screening, it's burn-in testing, or whatever. Always there's the same target, to catch the weak population. So when your production produces these weak units, you need to find them in order to get rid of the infant mortality. So from the bathtub curve, you try to verify that none of those products which would fail early in the lifetime would enter the market. So there are two questions, and the first question is, what is the correct amount of stress which you use to find the weak units? So now these are coming from this Anthony Chan's book, but basically this is just the same stress strength diagrams what we already have, but now we have so that the product strength is here in the y-axis, and the stress exposed to the product is in the x-axis. So basically this line, x equals y, is when the stress and strength are equal. So meaning that if you are below this line, then something is failing. If you are above, it's not failing. So here the strength is higher than the stress, and here the strength is lower than the strength. Strength is lower than the stress, so it fails. So defining the screening stress level is quite simple if we have this kind of thing. So we have very small weak population where the weak population strength is much below the average of the main population. And this distribution is rather narrow. So there's a basically huge difference here. So then we just pick up this stress level, which is just above the strength of the weak population. We will find these and we will let these go to the market. So that is simple. But the question becomes, so we can say that here we have a very robust product. So we have designed it so that the main population, the average strength is way above the average stress. But then what if we have this kind of a, let's say, situation that the weak population, the average strength is only not that much lower than the main population, and the main population has a relatively large variation or scatter. So this distribution is very wide. So it means that if we pick up this stress level, arbitrary number 2, then it means that, okay, we can get all the weak population out, but still we have this part here where the stress is higher than strength. So these cause then these early wear-out failures, meaning that these are leftovers, which means that this specific part of the population, the weaker units in the main population, will face stresses which are maybe higher than on average, so they will fail. So this is related now to the acceptable failure rate. So if you can allow that certain amount of your products will fail early in the lifetime or during the normal operational life, then you can use this kind of a stress level and just cut these off and then accept that, okay, there will be every 100, one product out of 100 or one product out of 1,000 will fail during the normal operational life during the first 3 years or something like that. Then it's okay. But if you cannot allow that, so then you want to cut also these away. So your acceptable failure rate is very small. So you have some safety critical product or whatever, then you need to use this kind of a stress level in order to cut this part away. But this also means that you are cutting away also this part. So you take out relatively large fraction. These would be the products that have lower strength, but they would never face this high stress. So as again, Above the line, it's no failures, and below the line, it's a failure. So in order to avoid these failures, you also get rid of these products which would not fail because they wouldn't see that high stresses, and then that's of course a cost issue. You now cut too large fraction of from the population. So now in this case, you don't have a, let's say, correct answer. The correct answer would be to push this one upwards. So make some design changes, material changes in order to have it more robust, or you control your production better so that this distribution, even the average strength or mean strength would stay the same, but the distribution would be much more narrow, like in the first picture. So that the definition of the correct amount of stress is critical question. And then the other question is that what about the stress which you use? Does it also harm those, let's say, products which are not failing during the screening and are going to the customer or markets? Does it have any effect on that? And now you need to remember these different types of stresses again, or failures again. We had these stress failures, and we have these cumulative stress failures. So for the threshold stress failures, it's easy, because let's again pick this very simple example of capacitor and how much voltage it can withstand. So basically you have a capacitor, and it's specified that it should withstand 1000 volts. And if you exceed that one, then it burns. If you stay below, then nothing happens. So you can easily go in the testing to go 950, and only those capacitors which have some hidden failures, they will burn. But basically for the good ones, this does not make any, let's say, defects or anything like that. But if we think about cumulative stress failures, like high temperature exposure or thermal cycling or whatever, then every cycle causes something. So even if you have specified that these products should withstand 150 degrees centigrade, then you go in your testing to 140 degrees centigrade, but also already that 140 degrees centigrade does something for the product. Something is changing there, and therefore it is basically means that what kind of stress level you can use in order to minimize that all these main population products are not significantly going downwards after the test. And this kind of a rule of thumb is that you can accept 5% decrease in the lifetime if 95 is left after the test. So of course this is just an arbitrary number. It could be as well 1% or it could be 10%, depending on the let's say criticality again of the product. But anyway, so you need to accept that small change in the average of the mean of the distribution is going downwards. But how much you can accept, that's the other important question. So it's enough that you just remember these two basic questions. What is the correct stress level to find out the weak population and get rid of the early wear outs or random failures, and what is the effect of this stress for the main population which you want to pass through to the customer. Okay, so then just a few examples. So as you remember, maybe you remember this picture from the HALT presentation. So here we defined with the stress step tests these operational limits and destruction limits, which of course should be higher than the specification limits. So this is what your customer wants. And then you can use these operational and destruction limits also to define your screening limits. And they were here. And now let's go look a little bit. I have in 2 slides, I have an example how these limits could be utilized. So basically, this is the same what I have already mentioned. So we want to find those units which have some hidden defects. Typically, you use, of course, lower stress values than the destruction limits, because otherwise you would destroy your products. But what is the correct amount of stress? That is really difficult to define. But for example, if you have done this highly accelerated life testing, you can use these values to define your highly accelerated stress screening. And then you need to define that do you do this screening test for all products or only with the sampling basis? So is it so that you are producing every week 1,000 products, and all these 1,000 products you need to screen to find out the possible defective units? Or can you do it on an audit basis? So this another acronym, HASA, highly accelerated stress audit, means that you just pick, let's say, every 10th product or every 100th product from the production, and you test that one, and then you assume that all the other 99 or 90 products have the same property. So you are kind of only monitoring that nothing is changing in the production, so that you assume that, okay, if this product which we produce today is good, it does not have any hidden defects, then all the others are also. So it means that, of course, you can save lots of time and money because you don't need to screen all the products, but also you need to verify that your so-called pre-screened reliability is high enough. So you need to have a high confidence on your own production. So it means that 90% of the products which you send to the customer are not screened at all. So you rely on your statistical process control. And now that is also very, let's say, big decision to do. So it might be the requirement might come from your customer that they say that, okay, you need to screen all your products. We are not purchasing your product if they are not screened. And or it is based on your own, let's say, reputation. So you allow these non-screened products to go onto the market, but you need to be sure that, okay, the quality, production quality is high enough. Or it's some kind of a compromise. So for example, you do on an audit basis, every 100 or every 1,000 unit, you have a more thorough screening. So you go through everything, and for the rest, it's much more simple. Like you just, after assembly, you just switch this one on, test it's working, okay, let's put it to the market. Not that you would test all the functionalities of the product with different stress levels, which is of course much more time consuming, but could bring up the possible, let's say, quality issues. Okay, so here is an example that how, for example, could this kind of a stress screening process be if we utilize the limits which were coming from the HALT testing. So now you see that here we have the, let's say, temperature in y-axis, and time is here, and here we have the vibration. So, and here is the operational limits. So upper operational limit, lower operational limit, upper destruction limit, and lower destruction limit on the basis of the temperature. And here we have the vibration. So the idea in this kind of a screening is that you have only 2 cycles. So first cycle is something that you go below the operational limits, but you stay within the destruction limits, of course, because you don't want to let the smoke come out from your product. But basically, you don't monitor here. You just do one cycle. You have a very high rate of temperature change. You go to the above the upper operational limit, or in this case, you go in the halfway of operational limit and destruction limit. Same for the cold temperature. So you go into the halfway of operational limit and destruction limit, and you use the also from the vibration, you use the halfway of the destruction limit divided by 2, so 50% of that, and then you have a stepped acceleration, so vibration loading like that. And then you do this kind of one cycle without any measurement. Of course, you cannot measurement because you are outside of the operational limit, so you cannot measure anything. And then after that, you make sure that the product has recovered, so no permanent failures. And then you do another cycle where you have, let's say, more slower rate of temperature change, like for example, 20 degrees per minute. You stay below the operational limits, so these values are the same what was in the thermal shock in the actual halt process, and then you have the vibration loading is operational limit minus 20%, and you divide that one to cycles, and then you can monitor throughout the whole cycle. So hopefully you got the point. So first, exceed the operational limits, check that no permanent failures without monitoring, and then the second cycle, you stay within the operational limits, use certain parameters which are defined here. Of course, you can use something else, but the point is that you need to stay below the operational limit so that you can monitor throughout the whole cycle. And then here, you put a stamp, accepted, can go to market. Okay, so basically now this concludes our discussion on the stage gate process. So we had, let's say, 4 or 5 different steps: reliability mathematics, highly accelerated test, and screening test. And all these have different purposes and different methods. And hopefully now you understand those. We used mainly temperature and mechanical loading in order to let's say, explain the purposes there. And now we start including the environmental effects. And again, want to emphasize that now environmental in the second part of the course means that we include humidity and then impurities into our testing schemes.